Hi, this is Beverly Owens with Lab Section M03, talking about Lab 7, the black hole mass. The problem is that we are estimating the mass of the black hole using the results of our analysis and assuming that the net force on the system is due solely to the gravitational force of the black hole. The main result is that we are analyzing the rate of change of momentum and of force, while analyzing the parallel and perpendicular components of each to predict the path of the star as it orbits the black hole. This will allow the mass of the black hole to be found by using Newton's gravitational force equation. Curving motion is also analyzed in this problem, and this applies to the momentum and the change of the star's path. The perpendicular force turns the momentum in a new direction and points towards the center of the kissing circle. The perpendicular force is represented by the black arrow. The net force, represented by the red arrow, always points towards the black hole, because the black hole is the only other object interacting with the star. As the motion and path of the star are getting closer to the black hole, the more curvature exists when the star is closer, because the radius is decreasing and the force is greater. The parallel force, indicated by the blue arrow, makes the momentum increase or decrease. This causes the direction of the star to reverse at a turning point, which is the closest location on the star's path to the black hole. The picture given is what VPython gives me when I run my model. The black dot representing the black hole, the arrows representing the appropriate forces, and the red line indicating the star's path. The computational model successfully predicted the mass of the black hole when using Newton's gravitational force equation, which is the magnitude of the net force is equal to the gravitational constant, which is 6.7 e to the negative 11, times the mass of the star, times the mass of the black hole, all divided by the magnitude of the position vector squared. Because our unknown is the mass of the black hole, the equation is rearranged, and when calculated, this gives us a mass for the black hole equal to 2.202 e to the 31 kilograms. The data given for my problem was a star mass of 1.989 e to the 30, a time step of 86,400 seconds, which is representing 1 day, and a black hole position at vector 4e to the 10, negative 4e to the 10, 0 meters from the origin, which is 0. I updated the VPython model from the previous lab to allow the calculation of the mass of the black hole. This was done by adding the gravitational constant g, which is equal to 6.7 e to the negative 11, the black hole position vector, and the black hole mass. The black hole mass was to be calculated with Newton's gravitational force. And in VPython, I entered the magnitude of F net times the magnitude of the star dot position squared divided by the gravitational constant times star dot m. This model fits well with the data if only the gravitational constant was acting on the objects in the system, and only the star and the black hole were in the system. The model fits the data poorly if the system consists of objects other than the star and the black hole, because other objects would exert forces on the star, possibly changing how the star moved around the black hole. So what does it mean? The F net, F perpendicular, and F parallel components are all related to dp dt, dp dt parallel, and dp dt perpendicular from the momentum principle, and the vectors being equal to each other. Because if you know the net force, you know how the momentum will change, and you can therefore update the momentum. This does not mean that the force and the momentum components are equal to each other. The momentum change is just caused by the net force. This leads to a difference between the two, that you can visualize the change of momentum on an object, but cannot observe the force acting on the object at all times. For the what-if question, you could not tell the difference between the new mass and the original mass of the black hole. Because nothing in the system is changing, there is no change in the motion of the star or the gravitational force. So this implies that the difference between the new and original masses of the black hole are not changing as well. This is similar to a difference between a pound of bricks and a pound of feathers. They are different items, but they both weigh the same, so their forces exerting on other items would not change.